This is video 41 in a series on single agent search. And in this video, we're going to be continuing to look at constraints in search. And we're going to look at them particularly in the form of something which is called bounding boxes or geometric containers. And the premise of the idea here is fairly straightforward, so this won't necessarily be the longest video. But this is an idea that was originally introduced by Wagner in 2005 of geometric containers. And then this is an idea that was reintroduced. Steve Rabin actually came up with this idea and was trying to use it combined with jump point search. And I helped him out in some of this work as well. And then there's actually a journal paper by Daniel Harbour, which is either has just come out or is about to come out, that looks at constraints and looks at bounding boxes and actually analyzes in some detail some ways that they can be even improved beyond what I'm going to talk about here. So if you're interested in this, interested in applying it efficiently, then I strongly recommend going and looking at that journal article, which has quite a lot of detail and really has the current state of the art. But I'm going to introduce the general idea here. And the first thing we want to think about is this question actually of what is a constraint. So we've been thinking about constraints. We were thinking about jump point search as it was putting new constraints on top of a state space, so a regular grid map. And we can put these constraints on it that say, well, I have to follow the canonical ordering. I'm only going to generate the canonical ordering. And given that constraint, then we can ask the question, should I generate another state? And so generally, where a heuristic gives me information about the distance to the goal, a constraint is going to ask, can we or should we generate a successor? Okay, so constraints are powerful because they can reduce the branching factor of a state space. And when I ask this question, typically we think about a heuristic. We say, well, give me a start state and give me a goal state. And then, tell me, or a current state, and you give me a goal, then I give you a heuristic back. Constraints typically might use quite a lot more information. For instance, we might use the start state or the goal state. We might use a heuristic as part of this. We might use the current state. We're typically going to use the current state, but we might also think about the current state or its parent. And there might be other types of constraints that would need other information that could be more complex. But the idea is that constraint is going to take some amount of information about a state space, and there could be other things that we'd want to have. For instance, just pre-computed data. And we're going to take this all into account to decide whether or not we should generate a successor. And typically what we're trying to do here is we're trying to prove that if I don't generate the successor, I'm still going to be able to find optimal solutions. So as I said, we're going to look at bounding boxes or geometric containers. Geometric containers, these are basically the same ideas. Geometric containers were only tried originally in, were mostly tried in using Dijkstra's algorithm in road networks. And then bounding boxes are basically a specific type of geometric container. So this is, in some ways, is a more generic approach, but then these were combined in an efficient way with jump point search to get big gains in performance. So let's talk about what a bounding box is. So it's a constraint. And basically it says for the input, if I'm thinking about what I'm querying here, the input is going to be a state, the current state, and an action. And the output is going to be a bounding box. And what it's telling me is it says, if I am in this state and I take this action, I'm going to give you back a bounding box, which will tell me where are the locations of the goals that you can reach optimally by being at this state and taking that action. So it's a bounding box possible goals that can be reached optimally. Okay. And so there's sort of a naive way we can do this. There's some theoretical work that says we should be able to do better. And in practice, yes, as I said, this recent journal paper by Daniel Harbour, he's one of the many authors on the paper, is actually saying, hey, here's some of the ways we can do this more efficiently. But generally speaking, what we're going to think about is, well, I'm going to follow through in the state space. I'm going to think about where, so the naive way, I can just do all pair shortest paths. And I can think about, well, what are all the states and actions which would be on an optimal path? And then when I'm generating a successor, so at runtime, I'm solving a problem where I have a goal state. So what I'm going to do is I'm going to query when I'm going to generate a potential set of successors. So I have, a state, I have potential set of successors here. And I'm going to ask the question, if I'm in this state and I take this successor, take this successor, anyway, I choose some successor, I'm going to say, where is the places of where the goal could be if I'm in this state and take this successor? And so that's, it's important because clearly, like if I come to a state this way, and I don't even keep the parent in here, so the amount of space this takes is the branching factor times the number of states in the state space. So it's a constant overhead, assuming that the branching factor is constant. With a constant overhead, then what I'm going to say, well, look, if I came into the state from here, I want to come out here, I'm probably going to get pretty good information. I have the potential of getting very good information about where the goal, or where the goal is going to be that I can reach using that action. Okay. And so I'm going to show two examples of this. And as we look at these two examples, what we're going to see is that there's a couple different ways we can do this computation. And particularly when we build upon the idea of a canonical ordering, canonical orderings are going to allow us to build much more efficient bounding boxes than we'll be able to do if we don't have canonical orderings for some cases. So we'll show some examples of that. So let me go ahead and pull up a window here. So this is a picture, and what we have, I think it's going to animate in, there's the start state is the blue cell there. And what we're showing here is what's the result of taking the right action. Okay, if I move to the right, and this says if I move to the right, the orange states are all the states that I can reach optimally, with the first move being moved to the right. So I move to the right one, and then, I can sort of I'll reach this optimal paths from that state to every other orange state in here. So from the parent, which is in blue, the child, which is the first state moving to the right, and then, of course, anything else that I could reach. So we notice that if I move to the right from the parent and then move directly up, then that node isn't part of the orange states because I could move there diagonally in one step. But our bounding box, instead of sort of trying to store all the states directly, we're summarizing all these states by having a complete bounding box of what is reachable and what is not reachable. So this is a pretty big bounding box. In this particular example, it's actually not going to help me very much. But if I go look at the same problem with a canonical ordering, I actually get something very different. So what does the canonical ordering give me? What I see here with the canonical ordering is once I move to the right, I'm not allowed to move down anymore. And so on this particular state, it was chosen because it's actually right on the edge of the obstacle. We're going to go straight until we hit the obstacle, but with the canonical ordering, we're going to get a jump point that's going to push us up into the top area of the map. But there's nothing that would push us into the bottom of the map. If it's going to go to the bottom map, I'd actually have to go diagonally down to the right. And so what happens is by putting a canonical ordering in here, I'm going to get a much smaller bounding box than I would if I were to not use the canonical ordering. And I'm just going to show one more example here. So it's a little video. In this video, what we're going to show is we're going to show for the different directions. So basically, on this map, if I don't use the canonical ordering, we're not going to show that in this video, but if I don't use the canonical ordering, then the bounding boxes will be these large bounding boxes that I get from my diagonal actions put together. But when I use the canonical ordering, then when I move in a cardinal direction, I actually get very small bounding boxes. So let's look at this here. I'm going to get very small bounding boxes moving in the 4 cardinal directions. In the diagonal directions, I just get what I would get from the diagonal directions. And so what this means, here we're going to do a regular A-star search on this particular problem using an octile distance heuristic. There's a massive amount of work that's needed to solve the problem. But when I solve this exact same problem using bounding boxes, we actually, and this problem of course is particularly good for bounding boxes, but in this particular problem, we actually only generate the optimal path from the start to the goal. Notice that there's no other states that are even on the open list. The only path we generated is exactly the optimal path. And why is that, may you ask? Well, if we choose any state along this path and think about any other direction that we could have moved, we can very quickly see that that direction could never lead us on this optimal path. And so, like if I start at the start state, I move to the left, that's not going to reach very many states optimally moving to the left, because to get to the goal, I'd have to move back to the right again. So from the very start state, all the actions of moving to the right, up to the right, to the left, moving down are immediately pruned away. We know we immediately must move down and to the right. And so there's a demo for this that you can actually run. You can compute exactly on this map. It'll pre-compute the data for you. You can choose different start and goal states. You can visualize the canonical ordering. And you can visit using the canonical ordering, you can visualize the bounding box from any particular state facing in any particular ordering. And you'll be able to see exactly the data that is pre-computed, and then the effectiveness of that data on reducing the size of the search. But overall, just to summarize here, is we've seen the idea in this short video that we can have the idea of introducing constraints. So constraints are this idea that tell us whether or not I should generate a successor based on some information. For bounding boxes, we're going to just ask, so the input is going to be the state and the action I want to take. We're going to get back a bounding box. And at runtime, I'm going to ask for each of my actions relative to the goal. So we have some goal here. Relative to the goal, we're going to say, look, is the goal inside the bounding box for a particular state and action? And like on an empty map, it's going to be the case that only this action right here with the canonical ordering, only this action is going to be able to get to the goal. This action here is going to be forced to go across and can never reach the goal. So by keeping this information and knowing where the goal is, then I'm only going to allow the actions that include the goal as a set of possible states that we could reach given that particular action. And so bounding boxes are able to prune the state space and are one example of a technique that can do this pruning very, very effectively. And so, as I said, I would encourage you to go find this recent journal article and look at that to see the complete details of how you'd implement this. But these are just a first example of where we get constraints. Something to think about, just as a challenge question, is thinking about when will our bounding boxes fail? What sort of problems will our bounding boxes be large? So that's an interesting question. I'm not going to discuss it here, but I think it's a challenge question to consider and follow up.